Okay, let's begin. Hello, everyone. Good morning and welcome to this talk, which is titled From Bulb to C Sharp. My name is Adam Furmanek and I will be your host for the next 1 hour. And greetings from Europe at the same time. In my time zone, it's around midnight. So if you are sleepy because it's morning, then I'm sleepy as well because it's night for my time zone. What we are going to discuss for the next 60 minutes is we'll see how the computer works, how these machines, which we use every single day, how they are constructed, how they work under the hood, and how it's possible that we can actually program them, write some code, and execute the things we would like to do. So we won't be covering actually anything which we typically do in our day-to-day work, right? We won't be covering high-level code. We won't be covering even low-level code. What we will see today is more of like a physical aspect of computers, how they are constructed, how it's possible that they actually can perform some calculations, exchange data, store things on hard drives, etc. And at the same time, it's not going to be a super complicated or requiring a very deep knowledge, nothing like this. We will start with some good intuitions and we will see that we can actually build a computer using any single light switch. Or if you ever read like a book, Free Body Problem, you could even build a computer just by waving hands as it's described in that book. So that's the idea. And before moving on, a couple words about me. So I'm a software engineer. I was currently working at Amazon doing some machine learning work. I was also a backend, front-end, mobile, and desktop application developer doing plenty of stuff. I have a blog at blog.adamfurmanek.pl. Feel free to take a look if you are interested in like math or internals of couple platforms, operating systems, etc. I'm also an author of .NET Internals Cookbook, a book which explains some internals of the .NET platform, available at Amazon. Feel free to take a look. Drop me a line on Twitter, email, whatever works for you. Feel free to ask questions either in the WebEx chat we have here or on the Slack channel. I'll try to answer the questions during the talk as we go. Okay, so agenda for this presentation. Well, our goal for today is we would like to build a computer. Probably not something as developed or as complex are the computers we are using currently, but something definitely capable of performing calculations, storing some data, and doing some logic, doing some actual like operations, conditions, loops, and all these things. And we'll start with just light switches because at the very bottom of everything, we can think of transistors or of the current as basically a light which is in the bulb. So we'll have some bulb emitting the light or not, and we'll starting from there, we'll go and finish with some actual computer. Then we'll cover some physical aspects of semiconductors and why we use them at all. And then we'll quickly move through the more things or more standards which were built on the physical components and giving us the things we have right now. So we will see a bit of history and we will see how all these things work together to do what we want to do. Let's begin. So bulb is all we need. So let's start with this pretty simple example showing the idea of what we are going to do today. So we do have a piece of wire and we do have a battery, which is basically a source of voltage. And we have a light switch, like a light emitting bulb, which can be either in on or off state. So this is where we start. And you can see in this wire that we have an ability to basically open the circuit or close the circuit here. So we can control whether the light is turned off or it's turned on just by, connecting two pieces of wire together. So this is where we start. And because you're probably programmers, and then you probably know that we can interpret like no light as signal 0 or as value false, and a light being emitted as value true or as signal 1 or as like a high voltage or something like this. This is where we start. And the first thing actually which was invented or which was invented pretty early is a thing which allowed us to communicate. So imagine that you would like to communicate with your friend sitting probably next door, next street, or maybe next city. What we can do is we can just take two light switches and we can connect them using wire, which probably could be pretty long, depending where our friend is. However, the whole principle stays the same. Now we do have some wire which we can like turn on and turn off in these two places. And like when we connect this piece of wires here at this point, light is being emitted using this bulb. If our friend connects the wires here, the light would be emitted and using this bulb. So what we can do now is we can take these two light switches, keep one with ourselves, put one in our friend's room, and then pull this whole cable and bang, now we can communicate. And obviously we would have a pretty simple signal just to send, which would be like a light, which we then could interpret in any way we would like to. For instance, you probably heard about the Morse code, so we could be like by sequence of lights of different length, we could be sending like letters, digits, or basically any transmission we would like to do. And it is as simple as that. And if we ever actually thought about the telegraph works like this. This is exactly what telegraph does. We just have a probably potentially very long wire, which is then connected or which is then allowed to pass some voltage using this button on one end and probably using some electromagnet, which is like making sound or turning on some writing machine on the other hand, or whatever else making a buzz. And this is how telegraph works. So if you ever heard about like intercontinental communication using telegraph, it's based on this super simple principle, which we could just use or apply by taking light switches and moving on. A couple words about notation here. You probably see, like with this circuit, that we do have basically a full loop of wire, right? You can see that this wire, like let's say it starts here, and it basically goes in this big loop, right? This is what we typically do, and we typically also indicate this, would like to indicate the source of power using the battery. However, because every single circuit will have these things like the positive and negative side of the battery on the closed circuits and yada yada, we typically make our notation a little simpler. So what we do is we indicate the source of the voltage as this letter V, and also we indicate the other side of the wire as being ground. You could physically just connect this wire like from your place starting here to the place like of your friend home, just by using a very big physical pole, which would be physically in the ground. This is where the name comes from, but we won't be getting into these details. Just keep in mind that from now on, whenever we do have letter V, it is basically a battery giving us some power which we can use to emit light from any of the bulbs we have here. So now, just by having these two light switches, we can start constructing something a little more sophisticated, a little more complex. And if you ever programmed in any language, basically, you probably know the operators like conjunction, disjunction, negation, or whatever else. And we will start by building these operations using light switches. So what we are going to do first is we are going to build the so-called AND gate. And if you ever heard about AND gate in like transistor level, we'll get to that. For now on, we'll be just building the gates using light switches. So the AND gate here would be basically a very simple, right? We would have these two switches on a piece of wire. If they are together, like if they both are closed, so the circuit is closed, then the light would be emitted here, and the circuit would be closed, right? However, because we probably in the integrated circuits or the designs, we are not going to use these light switches or whatever else. We need to have some other notion or some other way of specifying that what we want to build is basically the circuit which represents the conjunction of two variables. And this is called the AND gate. So this gate is represented as this like letter D with two inputs and one output. And you can see that basically logic for this, or the rules for this gate, is they are super simple. Just like in your any language you use, like C#, you have two Boolean values as the input, and here represented as 0 and 1. And the AND gate emits signal on the other end only when both inputs are true. So you can see here that the output signal we would interpret using light switches as basically light being emitted or not, right? So if light is emitted, the output signal is interpreted to be 1. If the light is not emitted, output signal is interpreted as 0. And input signals here are basically these two switches. So this is how we could build an AND gate using just a piece of wire, a battery, and a light switch. Similarly, we could build an OR gate using similar principles. So this time, because OR gate emits the signal when at least one of the inputs is on, so we basically need to connect these two wires in this way. So if any of them makes the circuit closed, then the power would go through the circuit and the light would be emitted. So this is how we built two basic gates, namely AND gate and OR gate, so conjunction and disjunction gates. Now comes the question, how do we make another gate, which is basically an inverter? So negation. And for inverter, we basically need to do some magic. So there is some voltage, there is some current going to the circuit, and on the other end, it's not going out, or the opposite, there is no current entering the circuit and then it's going out. And to build this, this gate, we actually need yet another component, which here is basically an electromagnet. So what is happening here is we do have this input here, which is basically whether there is current flowing through to the electromagnet from here, but there is also actually a separate part of the circuit which is flowing through the starting here and flowing to the bulb. So whenever this one thing is turned off, there is no electricity flowing through here, so the circuit is closed at this point. However, imagine that we now close the circuit here. So there would be a wire connected here. We would have some electricity flowing through the electromagnet, which would effectively, because it's a magnet, it would make the other switch to just bend a little, which would open the circuit at this point. So it would stop emitting the light. So this is the principle behind building the NOT gate, so the inverter gate. So we can see just by using, again, battery, piece of wire, and bulbs, and the light switch, we need one more thing, which is basically the electromagnet, and we can build the inverter gate. So now we have three logical operations built using only the bulbs, which is conjunction, disjunction, and negation. We can build a couple more slightly more sophisticated gates. For instance, the NOT OR gate, which is basically working as an disjunction of two variables. So it's like an OR of two variables and then negation. So this NOT OR gate, it will emit one on this side only when both inputs are 0, right? Because we will take OR of these two things, which would be still 0, and then we negate them at this point, and that would be 1. For NAND gate, pretty similar. We just take the conjunction of two signals and then we emit something. So we will emit 0 here only when both inputs are ones. So because we have conjunction of two ones, it would be 1, and then we invert it so it becomes 0. And again, the last gate we could build here is basically the exclusive OR, which emits 1 if and only if exactly one of the inputs is non-zero. So if exactly one of the inputs is true. You can see that we can, just by taking these three basic gates like conjunction, disjunction, and negation. We can start building couple more sophisticated gates. Actually, in like designs on the low level, we typically start with one of these gates, like not AND gate, and we build other gates out from this one. But this is like a digression. So this is what we built, okay? We can see that we started with the light switch, piece of wire, and electricity. We could send a signal. Now we can start modifying this signal to some extent. We can do some logical operations. Obviously, we'll probably need plenty of the light switches if we want to do something, or plenty of these gates constructed from wires and batteries. But technically, it would work. What can we do next? Well, we can start doing some logical operation, or sorry, some arithmetic operations, and we can start building the so-called half adder. If you remember from ground school, whenever you do the long addition, like addition, adding two long numbers, what we typically do is we add them digit by digit, and we have carry, which we include when adding the following digits. We can do the same, obviously, on a binary level in like binary system. And the first thing which we need to build is the so-called half adder, which will just add the two digits and then emit both the sum of these digits and the carry. So you can see that just by using the exclusive OR gate and the conjunction gate, we can calculate what we need. Because what we want to calculate is, first, we would like to have a sum of these two inputs A and B here. So you can see that if you calculate this in binary, this sum will be 1 if and only if exactly one of the inputs is set to 1. If we add two ones, then what we effectively get is we get the number which is 2. So it requires 2 digits to be encoded in binary level. So first the lowest digit will be 0, and then we'll have the carry, which will include in adding the next digits in order. So this is half adder, which is also typically depicted as this like rectangle named half adder with inputs and outputs. And then using half adders, we can start building the full adder. And the full adder is only slightly more complex, because what full adder needs to do is it takes the digits which need to be summed together, but it also takes the carry bit from adding previous two digits. So what we have here as an input, we basically take two digits to be added and the carry bit from previous addition. And what we do next is, again, for sum, we do some magic using the half adder, and for carry, we basically need to include carry from both additions here, because effectively here we are doing like two additions in one go. So this is again depicted as something like this, or this can be depicted as one unit, which is basically an adder. And you can see that once we build this thingy, what we can do next is we can build a series of these adders, because this particular adder, it only adds 2 bits of like 2 bits, right? It doesn't add like 32-bit long integer or something like this. It just adds 2 binary digits with 1 carry. But if we would like to sum integers which would be 8 bits long, 16 bits long, or whatever else, what we need to do is we need to basically put a series of these full adders, and then we'll get each bit, we'll extract each particular bit of the sum, which we can then use to reconstruct the full result of addition of like 8-bit integers. So this is how we build the arithmetic operations. You can probably imagine, we won't be going through more details, but you can imagine that subtraction will be based on a couple similar ideas. And once we have addition and subtraction, we can build multiplication, division, yada, yada. So we can take for granted from now that we do have some Boolean logic, because we know how to do conjunction, negation, etc. And we can do some simple arithmetic. We can add numbers, everything just using light switches. Now we are probably, to simplify the notion, we are just using gates, but you know that these gates can be built using a simple light switch with piece of wire and a battery. Moving on. What we would like to do next is we would like to have a clock, because our CPUs, they do have some frequency, right? So how do we build a clock? Well, we build a thing which looks like a very counterintuitive circuit, but in fact, it's pretty simple. So we start with, similarly to negation, we do have an electromagnet here, but we do have a circuit which is like a single loop here, which is closed, which goes like the input of the circuit is at the same time the output of the circuit. So what happens is, in this oscillator which we are building, is we start with something like this. There is no electricity in this circuit because, well, the circuit is opened here. What we do next is we would like to close the circuit here. And once we do it, because we do it, the circuit is closed, as you can see here, the electricity starts flowing through the circuit. However, the moment the electricity starts flowing, there is the electricity here in the electromagnet, right? So because there is electricity here, it pulls the switch here, so it opens the circuit, and we end in this position. Because now the circuit is open, there is no electricity in the electromagnet, so this switch will just return to its original position because, let's say, there is some spring or whatever. So then we will basically go again to this situation because this switch will be closed, so the electricity will be flowing. There will be electricity and an electromagnet, which will then open the circuit and yada yada, over and over again. Obviously, because these are physical components, so this switch, which is here, it will have some physical delay between the time it opens and it closes. So it will have some inherent frequency, which is here. It may be too low for our needs. However, it will just work. So once we start moving or we execute this circuit, if I can use this word, this will work indefinitely, emitting like 0 and 1, opening and closing the circuit. So this is how we build oscillator. And this is how we typically depict the oscillator. So you can see that what we built here is the inverter gate, so the negation. And this is why it's super counterintuitive, because we do have the output of this gate is again the input of this gate. So it seems like it would never converge to some stable state. And this is what basically gives us the time, because it will be emitting low voltage, high voltage, low voltage, high voltage, and yada yada. So just by using this simple trick, which is counterintuitive, but well, it's pretty simple once we figure out what we are trying to do, we can see that we do have a time because we have a clock. We can use the output from here basically as an input to something else, and that would be a clock in our system. So we do have Boolean logic, we do have arithmetic, now we have a clock. What else do we need to run a computer? Well, there would be one more thing which would be super useful for us. And this one last thing is basically a memory, because we would like to keep the memory. We are not talking here about a non-volatile memory like a hard drive or something like this. This is much closer to, let's say, some RAM memory, like random access memory, which can persist the bit for the duration of the when the computer is turned on. Once we remove the electricity, it can all collapse. So just like the RAM can lose its content, but this is okay for us because we'll be just using it for the calculations. So what we do here is we are going to build yet another slightly more sophisticated circuit in which we are using two NOR gates, and we are going to build the so-called reset set flip-flop. So we do have two inputs. One of them, actually, this one at the top is called reset input, and this is called the set input, and the one at the bottom is called the reset. So what is happening here is you can see that initially in the circuit, there is some electricity flowing through here. Why? Because we do have not OR gate, which is getting 2 zeros initially at the input, so it must negate it, so it's emitting 1. And the other NOR gate is emitting 0 because it has one non-zero input. Once we want to set the bit of this memory, and our memory is basically this light switch. The light bulb is our memory here. Once we want to set it, we basically close the circuit here. So you can see that we do have, we do start by closing this. So then one bit changes to true signal. So then this NOR gate will change to 0 here. Because we will have 0 here, we will have 0 here, 0 here, this NOR gate will start emitting 1. And when this one is being emitted here, you can see that it's flowing as well here. So this circuit will converge to the state we have here at the top. So we will have two ones, 0 here, 0 at the input, and then finally one here. So this is where we start. This is what happens once we set the thingy. However, the important part of this is that once we are in this state, we can basically open this input. We can like open this switch, but notice that even though we did open this switch, because we do have one being as an input here, we still have the electricity flowing at this point, so our bulb at the very end remains turned on. So it remains emitting the light, and this is effectively that the bit remains being set. It is still turned on, even though we returned the circuit to the original state when it comes to the inputs. So this is set bit, how it works. When it comes to resetting the bit, what we would like to do is we would like to reset it here. So we would like to close the circuit here. We will be emitting 1 at this point. So then here at the very end, this will change to 0. So because this changes to 0, we will have 0 here, we will have 0 here. So then there will be 1 emitted here, and because of that, the circuit will converge to the initial state which we observed like here on the left, which is basically electricity flowing only here and the bulb being turned off. So this is how we can build the memory using, again, battery, a piece of wire, and couple light switches if needed. So what we have here now is Boolean logic, arithmetic, clock, memory. Now what we need to do is, it should be pretty understandable now, but let's make it pretty obvious. We'll skip this slide and this slide as well. What we would like to do is we would like to build a bigger memory. How do we build a bigger memory? Well, we know how to persist one single bit of memory, so we can persist multiple of them using the same principle. Just like we add longer numbers by putting together multiple others and half others, the same way we persist more memory just by using more flip-flops to do the magic. And now what we would like to do is we would like to start building the heart of our computer, which is something like an if condition. So then it can recognize what the input is logically, and then we can start executing some instructions. So we will do a 3 to 8 decoder thingy, which looks pretty complex, but effectively, once you decipher all the gates here, it is super simple. Because what we would like to do is we do have an input, which is 3 bits of input, and we would like to basically build a very big if-else condition, which could tell us, hey, what is happening? Because imagine that now we are building a very simple instruction set of our CPU. So we do support 8 instructions, like addition, negation, subtraction, maybe some jump, maybe whatever else. So we do want to recognize, hey, what instruction we should execute. And in order to do that, if we were to implement this using like a C# language, the circuit on the left is basically doing this cascade of if-else conditions. Because once you figure out how these inputs here, these 3 inputs are connected to the AND gates here, you'll figure out that it's basically doing some some conjunction, checking whether we have like three zeros here or three ones here at the input, and only one of these outputs will be set to true. Only one of these outputs will be emitting the current, so only like one light switch would be on. And because of that, we can use only one output to figure out which instruction is to be executed next. You can imagine that, for instance, this output would represent like the add instruction. This output would represent something like negation instruction, etc., etc. So once we have this, we are done because we do have Boolean logic, we do have arithmetic, we do have clock, so we do have our frequency, and by using clock, we can, for instance, set the speed of our CPU. We do have memory, and we know how to recognize the instructions. And just this is all we need to basically build a computer. And just like you know how to draw an owl, you draw some circles, and then you do have an owl. This is how computer is constructed. Obviously, it would be thousands of light switches, especially if we wanted to do some actual computations, right? Because for actual computations, we probably need like a couple of registers, which are like 16 or 32 bits long, right? So we probably will need like plenty of light switches to represent them. The same for instruction set. 8 instructions for our CPU probably won't be enough. We'll need something like 100 instructions to do things efficiently. So the decoder would be way bigger and much more sophisticated, but the principle stays the same. Not to mention the memory. If we would like to hold, let's say, 1 kilobyte of memory, you imagine it would be 1024 bits. So that would be plenty of flip-flops to hold the memory. But apart from that, we know all the principles now, and we can effectively start building these things. So this is how computer starts, at least on the light switches level. Now, moving on to something a little more practical. I'm not saying that this is not practical, but you would probably require a very big room to build the computer using light switches. And this is how first computers were constructed. They were pretty simple in terms of size because, well, light switches, wires, batteries, they do occupy plenty of space. What allowed us to build computers like for real was the invention of the transistor, which could be built using the semiconductors. So when we take a quick peek at the physics level, we do have things which are called conductors, insulators, and semiconductors. So conductors, they do allow for passage of electricity, right? So these are things which we can use to basically kick the electrons. So the electrons are flowing through the wire, so the electricity is moving on. We do have insulators which do not conduct the electricity, and we do have semiconductors. And semiconductors are not called semi because they are working like half as well as the regular conductors. They are called semiconductors because we can modify their characteristic. We can dope them, combine them with some other particles, other impurities, so we can control how they behave. And then there was probably the biggest invention of 20th century, which was by Shockley, Bardeen, and Breton in 1947, which was the invention of NPN transistor. And transistor is a very tricky thingy which allows us to control the current by setting some voltage on the base thingy. And once we put the voltage on the base, we can control how much current is flowing through collector to emitter. Not going much into details how these things work, you can just assume or take this for granted that this NPN transistor can do this magic. And now once we have this transistor, what we can do is we can build everything what we built previously. So we can start by building gates. How do we build gates with transistors? The same way as previously. So previously we did have like a couple of, we did have wires which were connected like serially or in parallel, and we did have the light switch at the very end. This time, instead of wires, instead of light switches, we just use the transistors. but the principle stays the same. We just need to connect the wires in given way to basically build the logical circuit. And I won't be going through all we constructed previously. You can imagine that the same way we built the AND gate, the OR gate, we could build arithmetic, CPU, decoder for instructions, memory, yada yada. It all works on the same principle. But the advantage of transistors is that transistors are much smaller and they do not emit that much of a heat as light switches would. And even though they are pretty expensive, especially initially they were pretty expensive, we can prefabricate the ready-to-be-used components called chips, which are actually doing the things which we would like to do. So we can build a chip which is basically an adder capable of adding like 8 digits, 8 binary digits or something like this, or chips doing other things like if condition, yada, yada. We still need to think about the interconnections between transistors, and if we minimize or if we change our construction process to fit more transistors in smaller space, we'll probably need to deal with heat being emitted. But apart from that, this actually allowed us to build things in the proper scale, so we could finally build a computer which is small enough, capable of doing the things we need. And moving on, once we get to this point, so we can build a chip which is doing a simple operation like addition, we can start building more and more sophisticated chips or integrated circuits, which we can just, take off the shelf, buy them in the store, and start building something bigger. Just like in programming language, we take libraries for parsing JSON, for sending HTTP requests, and we use them to build something, some business logic. The same way here, we just take a chip which is adding numbers, and we can build something more. There are multiple technologies for building these integrated circuits. You probably heard the abbreviations like TTL or CMOS, and everything around that is basically how we build these things, and then how we can use them, what characteristics they have to when we are building the full computer. So this basically closes the physical aspect of it. And you probably realize that like the physical aspect, we could think of it as of like a learning how to program, like the basics of computer language, like C# language, right? But what we now need to do is we need to come up with patterns, like solid principles or patterns for our integration between nodes or in distributed system, or just basically the ways to build things efficiently, just like we build libraries or nugget packages in C#. So this is where we enter the world of computer architecture, in which we will basically see what other standards had to be built in order for us to finally land where we are now. So computer is basically something like CPU, so a unit which is capable of calculating things. RAM, as in memory, some memory where we can store intermediate results. Some way of getting instructions into RAM. So we do have some input device. It doesn't necessarily matter whether it's like a tape or a hard drive or whatever else, but there needs to be some input which we can use. There also need to be some output. Obviously, we could use light switches as an output. We could use like a monitor screen display for an output. We could use something else as a printer. But it means there is some output of the calculations we have. We could also use some non-volatile memory, which is basically a storage, like a hard drive. We could come up with other things which we could use here, for instance, network cards, which could be considered being an output device, or other things which probably we use every single day. But these are the things which we need to start with. And all these things, they need to communicate somehow. Now the question is how? We build the 3-to-8 decoder, so we know how to interpret what the input is and which instruction we should execute. But now comes the thing, how do we communicate between different devices, probably manufactured by different producers? What we can do is we come up with a bus. And just like the same way you come up with like enterprise service bus to connect your nodes or the HTTP protocol to connect your machines, the same way we come up with a bus, which basically is a standardized physical component which knows how to read the input, read the address, and deliver the data to some output. So we do have some bus which is connecting all the components, and CPU can use some of the registers of this bus or some of the physical inputs or basically light switches in our nomenclature for today to indicate what the address it wants to access, for instance, and what the instruction it wants to perform. So then bus knows how to deliver this thingy, for instance, to the memory unit. So then the address is delivered to the memory, and the memory component knows which light switches to read to return data for the CPU. So this is the thing, and the same way we divide or we come up with standards for like logical things, the same way buses had to be standardized. And there are multiple bus standards, especially initially in early days. All of these standards were completely incompatible, and they had to be, battle tested, and people had to realize which things can actually survive for slightly longer. So then we could build on top of these things, not to reinvent the bus every single time. And there are a couple, for instance, standards, for instance, the industry standard architecture, ISA, which was designed by IBM and which prevailed for a pretty long time. Once we have the bus, once we have the CPU, we now need to figure out how we actually logically put these components so they can interoperate. And we come to the thing called computer architecture. There are multiple architectures. One of them, which is the most popular, is called von Neumann architecture. So this architecture basically specifies that there is some arithmetic logic unit. It basically describes how we have the motherboard with north bridge, with south bridge, how these things communicate over bus, etc., etc. And the thing which is the most important here is that how we address the data and the instructions in our computer. In von Neumann architecture, both data and instructions are stored in the same storage, and they do have one address space, meaning that we can take some data and use it as an instruction, or the opposite. We can take the instruction and use it as a data. There are other architectures as well, even though von Neumann, we typically say that our computers are based on von Neumann architecture. It's not necessarily true because now our computers now are much more sophisticated. We do have especially caches, and caches are technically modified Harvard architecture. So just like we did say about the addressing in von Neumann, modified Harvard allows us to separate, or sorry, the Harvard separates the addresses for memory and separates the addresses for instructions. So this is Harvard architecture. However, modified Harvard architecture, which is used for caches, basically merges these things together. So these things are pretty flexible in terms of classification, how these things work. We typically say that our computer is von Neumann architecture. This is not super precise, but for our needs, it's good enough. So once we do have this architecture, which is basically like a logical plan of how we would like to build our computer, we do have a bus allowing us to communicate between the components. What we need to build next is we would like to focus on improving our CPUs so they work faster, better, support more instructions, yada, yada. And CPU architecture is basically a term which is used in multiple contexts. Typically, when we talk about CPU architecture, we think about the instruction set architecture, or even like more precisely, how big the numbers are. This is what we typically think like when we say our architecture is 32-bit architecture or 64-bit architecture. This is what we typically think of. However, it's not enough, because architecture specifies how the CPU works in general, what is the pipeline, what instructions are allowed, how instructions are executed, ordered, how fast they run, etc., etc. All these things are basically important for the CPU, and thanks to the long history of computers we have now, we don't need to think about all these things. However, in early days, in last century, all these things obviously were super inconsistent. Each CPU was running on different architecture. And now when you think that you have issues because your application is not portable from Windows to Linux, you typically do not have the issues which appeared or which were prevalent in previous century, which was like our applications were not compatible between two CPUs. Currently, all the CPUs, they are standardized for us, so we are happy enough to not think about that. But previously, like you could be writing your application using some very low level language, and then IBM comes up with different, or Intel comes up with new CPU, and you basically need to rewrite everything from scratch because instructions are completely different. So the instruction set architecture, what it specifies is it tells what data types are available, which registers we can use and how they behave depending on the instructions which we execute, how the hardware for memory works, etc., what the memory consistency is, etc., etc. All these things we can classify depending on the architectural complexity. And there are multiple like acronyms you may have heard of. For instance, we typically say that our computers or our CPUs currently, they run using so-called complex instruction set computer, so CISC instructions. So CISC instructions, if you ever like read the assembly code, you probably noticed that each instruction may have completely different length. For instance, the NOP instruction is just 1 byte, but for instance, jump instruction should be something like 5 or 9 bytes, depending whether you're running in 32 or 64-bit, because it's telling, hey, I need to jump, and then it specifies the address. And there are so many different instructions available to us in the CPUs. For instance, some of them are like for encryption, some of them are for calculations, etc. And Intel adds more and more instructions with each new CPU unit. Why is that? Because, well, we would like to do more with less instructions. If we can specify that like one instruction is for whole AES encryption, that's perfect for programmers, not necessarily perfect for CPU. Why? Because CPU, in order to run fast and efficiently, it would like to know exactly how long each instruction takes, and it would like instructions to be consistent. So that's why we do have some other instruction set architecture, which is called RISC, Reduced Instruction Set Computer, which basically uses like many less instructions, which are all typically of the same length, and they are much more basic. Like in CISC computer, we may have instruction which is used to encrypt the data using AES. In RISC instruction, we will have only basic operations like add two numbers or something like this. We typically say, just like with von Neumann architecture, we say our computers are based on von Neumann architecture. We typically say that Intel CPUs, they are CISC instruction sets. This is not necessarily true again, because under the hood, these CISC instructions are translated to RISC instructions. So effectively, CPU runs on RISC. However, for us programmers, what is exposed is the CISC instruction set. There are also other architectures like EPIC or very long instruction word, yada yada. Obviously, they were alive for some specific use cases, but now prevalent architectures we are talking about is are the architectures based on the 8086 processors, which we'll get to that in a sec. So a short history about IBM PC. So IBM and Intel, they were producing components which changed the world and shaped the future for many years. So in 1974, there was the 8-bit microprocessor called 8080. It was used by the first home computer like Altair 8000. And then based on this CPU, Intel finally decided to stop changing the instructions or architectures with every single CPU, they started maintaining a piece of compatibility with previous solutions. So they built 8085, which was 8-bit microprocessor fully compatible with 8080. And then 8086, which was a big step forward because it was 16-bit microprocessor, so it could address much more memory. However, 8086 was not compatible with 8080, and then 8088 was constructed, which was 16-bit and also which was compatible with 8080. And this 8088 CPU was used in the thing which we call the personal computer, the PC, which was 5150 personal computer built by IBM. So this is how these things started, and around this 1979, 1980, we finally had some architecture we could build upon and maintain the backwards compatibility, and this is where the x86 and AMD 64 architectures come from. So x86 architecture is 16-bit CISC architecture based on these old processors which we just covered, and then 32-bit extension was built by Intel, and this is what we call 32-bit architecture. Or typically we call it just x86, even though it's IA32, Intel Architecture 32, or x86-32 to be precise. Then Intel experimented with new architecture which was based on 64 bits. They called it IA64, and it was built on completely different principles. It was still capable of running 32 bits programs, but it wasn't as fast as it could be. So they dropped it because at the same time, AMD built the extension for 64 bits, which was called AMD 64. And this is what we called X64 now. So 64-bit architecture compatible with old 8080 processors. So then Intel took this AMD 64 extension, built their own Intel 64 or EM64T, yada, yada. And this is where we are now. Obviously, you probably heard about different architecture, which is called ARM, which is in your mobile phones. This is completely different from this thingy. This is completely independent, but you know the principles, you now understand what the difference might be between x86 or ARM. So the instruction set or how the memory is constructed, yada, yada. And that also explains why, for instance, when Microsoft released the Windows for ARM, applications running on the regular Windows were not like Windows was unable to run them on ARM. Why? Because these two architectures are incompatible, and this is incompatibility of on a very low level, which dictates basically anything which happens in the computer. So it's not as simple as just changing, Linux to Windows. It's actually much bigger thing to support. So this is where we more or less started. What also happens when we develop CPUs is we would like to have as powerful instructions as possible. So the SSC or other, for instance, AVX, they are basically instructions which are capable of doing more with less instructions. So for instance, they allow you to encrypt data using AES. They can add vectors. They can add very big numbers in one go. And the advantage of these instructions is they are executed physically, natively by the CPU. So they are pretty fast. We can emulate them using software, but it's much slower then. So even if your CPU doesn't support them, you may still be able to run your applications. However, it will be much slower than the native physical support. One example of this is when you are trying to virtualize something, like virtualizing your virtual machine. If you do have physical support, it is done by some instruction set in the CPU. So if you do have the support, then your virtual machines will run way faster. If you do not have the support, virtual machines will still run, but they will be much slower because things need to be emulated. And then it's time to finally cover a couple of different codes we have. So we typically say that we program in high-level code. So there must be also some low-level code. And let's go through all these codes starting from the lowest possible level. So even below the machine level code, which you can write on your CPU, there is a thing which is called microcode. This microcode is something which is implemented directly in the CPU, and this is also some different type of programming. For instance, in this microcode, things which are written are to translate CISC instructions to RISC instructions, etc. They are obviously completely not portable because they depend on the CPU you're running on. Implementing these things is relatively hard, more complex than implementing anything, even in like assembly language. But the funny thing or interesting thing is this microcode in CPU physical chips can be updated using like Windows or Linux updates. So basically, when you download Windows updates, some of these updates, they do go and update your CPU code. This is especially visible when we do have some security issues, for instance, Heartbleed or something else. There is the updates for the microcode of the CPU may be distributed or will be distributed using the regular Windows updates to enable or disable or change the things how they work. And this is something we, as a regular programmers, we cannot touch at all in most of the cases. Like we physically cannot touch this at all. Then we do have some machine code. This is the code which we written using our bulbs. So this could be seen as the composition of gates which we constructed initially during this talk. The machine code, which is different than the assembly language, because machine code needs to be even more specific. Like in assembly language, you just say, hey, add these two registers. But the machine code needs to be precise to specify exactly which registers, because there is different instruction to add registers EAX and EBX than instruction to add EAX and ECX. So it's rarely written by hand, mostly emitted by compilers, etc. Things are basically based on numbers, hard to read, hard to write, but we, in theory, can generate it, and compilers do generate it. Then we do have an assembly language, the typical assembler you have, so mov, add, sub instructions or the things. This can be accessed by the developers either in like kernel mode or user mode, so in the operating system level mode or the user space. Then on top of that, our operating systems, they do provide some API. Once again, some standards to simplify the way we implement things. One of the standards is a Win API. The other is POSIX. So we do have these standards, and this allows us to implement applications which are portable. So we can take the POSIX application from Windows to Linux or the other way, and in theory, they should work properly still. We can access this API obviously like directly using, for instance, C++ language or in kernel mode through drivers or whatever else. And when we are talking user and kernel mode, the difference between these two is just how CPU allows you to access like memory on or devices. We won't be getting more into details for this. This is just for security for most of the times. And your CPU initially, when you like press the power button, initially when you start your machine, the code which runs there needs to configure these rings and these modes so the CPU is protected from like malicious user space code. Then we get very high to the user mode native applications. So this is basically like user space applications written in some native language like C++ or Delphi. So these applications, they typically use something like C++ runtime or Win API directly or whatever else to do the job. So you can already see that there are so many layers under the hood for these native applications, as we call them. And then on top of that, we build the managed applications. So we build a managed platform like Java Virtual Machine, CLR for .NET or web browser or Python virtual machines or whatever else. They typically cover all the operating system functions and APIs with the managed API. So then programmers typically don't want to or don't need to access the low-level operating system APIs, right? We can do the interop thingies, but we typically don't need to because .NET covers all of that. And on top of that, on this JVM or CLR, which runs using bytecode, we get to the managed languages. So we could use CLR language directly or bytecode in JVM directly, and the platform would make sure that the application is correct, we do not crash the memory, etc. But we finally land with high-level managed language, which is C# or Java, which is typically portable, which covers all the quirks of the platform, hides all the details of the CPU. So to sum up, going from the high level to the lowest possible level, we write the application in some high-level managed language like C#, which is then compiled to low-level managed language like intermediate language on CLR, which then is compiled using just-in-time compiler to Machinecode running in user space, which calls the operating system functions like WinAPI. Then these WinAPI functions then switch from user space to kernel space. And in the kernel space, they typically run some assembly code, which is compiled to the Machinecode. Then the Machinecode is fetched by the CPU, translated to micro operations and to the microcode. And these micro operations are finally executed using the transistors or using the light switches where we started. So we made a very big leap from the computer which we built, but at the very end, under the hood, what happens there is we still have the same things: Boolean logic, arithmetic, decoder for instructions, some flip-flops for memory, and all these things connected with wires, with light switches, etc. to run the code. So even though it's constructed way differently because we don't use light switches, we use the transistors, we use so many sophisticated things to make this run fast, the principles, they are still the same. So summary, computer, even though it sounds tricky, once we start with these gates, it's relatively simple concept, and it took many years to cover all these simple concepts so they are standardized and we can use them together efficiently. However, now we are in much better shape because we are not exposed to all these things, even though they are still there, but we don't need to think about them. That's thanks to standards, and this is how computer science or software engineering typically works, that we build more and more abstractions on the lower level layers. Q&A. I don't see any questions here in the chat room. I don't see any questions in the Slack channel. Feel free to drop me these questions later in the Slack channel. I'm happy to answer all of them. And yeah, let's wrap this up. Typically, I recommend some books or some links which you could read to learn more about the things I covered. There is a fantastic book by Charles Petzold which is called Code: The Hidden Language of Computer Hardware and Software. Actually, images in this talk, they come from this book as well. And it really covers plenty of these things, and also is a very interesting read for the history if you would like to learn how hard things were back then, how these things evolved, how the standards were introduced. This book is really a fantastic read to understand all these things. And having said all of that, it's time to finish this talk. So my name is Furmanek, and I'd like to thank you for attending this talk. Hope you enjoyed it, and I wish you all the best and enjoy your day at NDC conference.